Okay, here's number 2. We're going to show that y sub 1 of t is equal to e to the 3t, and, well, y sub 2 of t is equal to e to the negative 2t, and a linear combination of these two functions are solutions of this ODE here. Okay, so this is our ODE sitting over here, and so we just have to check that each of these given equations actually satisfies the ODE. Okay, so let's start with y sub 1 of t. We have this is equal to e to the 3t, and we're going to need the first derivative and the second derivative, so let's just do that right away. So y sub 1 prime of t is equal to 3e to the 3t, and the second derivative of that function is going to be equal to 9 times e to the 3t. So let's plug these into our equation. We start with y double prime, so this is going to be 9e to the 3t. We plug that in there, then we subtract away y prime, so this is minus 3e to the 3t, and then minus 6 times the original function, so that's 6 times e to the 3t. Is this equal to 0? And the answer would be yes, because we have a 9 minus a 3 minus a 6, which equals 0, so 0 equals 0. And y sub 1 of t satisfies our ODE, so it is a solution. So now let's work with y sub 2 of t. This is equal to e to the negative 2t. So again, let's find our first derivative and our second derivative right off the bat here. So we have negative 2 e to the negative 2t, and our second derivative is going to look like this. We have a positive 4 now times e to the negative 2t. Okay, so let's plug these ones in. So we have 4 times e to the negative 2t minus a minus 2 e to the negative 2t, and then minus a 6 times positive e to the negative 2t. Okay, so this also equals 0 because we have 4 plus 2 minus 6, which is equal to 0. So 0 equals 0 again, and y sub 2 of t is also a solution to our ODE. So on the next slide, let's explore the linear combination of these two functions. So a linear combination of these two would look like this. So we have c sub 1 is a constant, right, times y sub 1 of t, which is equal to e to the 3t. And then we have plus c2, which is another constant, times our y sub 2, which was e to the negative 2t. Okay, so again, let's find the first and second derivative of this function, which is formed from a linear combination of our other two original functions, remember? So if we just take the first derivative, we just have 3 times c1, e to the 3t, plus, well, we'd actually have a minus 2 c sub 2, e to the negative 2t. And then we shall derive once more to get the second derivative here, and we'll get 9 times c1, e to the 3t, and then plus 4c2, e to the negative 2t. So let's plug this into our ODE, which was y double prime minus y prime, minus 6y is equal to 0. Okay, so let's check this. So we have our y double prime first, so we have our 9 times c sub 1, e to the 3t. We're going to have to squish this in here too, by the way. But we can do it. So here's our y double prime. Then we're going to subtract away our y prime, which is 3 times c1 e to the 3t, minus 2c2 e to the negative 2t. Then we subtract 6 of the y of t, which is c1 e to the 3t, plus c2 e to the negative 2t. And does this equal 0? We're going to write a question mark here. So let's group all of our corresponding terms. So we have 9 minus 3 minus 6 times our c sub 1 e to the 3t. And then we have plus 4 plus 2 minus 6 of our c sub 2 e to the negative 2t. Does this equal to 0? We have this is equal to 0, and this is equal to 0. So yes, 0 equals 0, and the linear combination, the function formed from a linear combination of the other two solutions is also a solution. Okay, so we have proved or shown all three of those are solutions to our ODE.